Our universe is a vast and mysterious place. From the smallest particles to the largest galaxies, there's always something that sparks our curiosity. Today, we journey into the heart of matter itself, the nucleus of an atom. This is the realm of nuclear physics, a science that unlocks the secrets of the universe's building blocks and their incredible power. Nuclear physics might sound complicated, but it affects our lives in countless ways. It's the reason the sun shines, providing us with warmth and light. It's the force behind nuclear power plants, generating electricity for our homes. And it's the key to life-saving medical treatments like radiation therapy for cancer. This journey will take us deep inside the atom to understand the forces that bind the nucleus together and the amazing reactions that take place within. We'll explore the world of fission and fusion, the processes that release unimaginable amounts of energy. And we'll uncover the mysteries of radioactivity, the spontaneous decay of atoms that has shaped our planet and continues to influence our lives. So buckle up and prepare to be amazed. The world of nuclear physics is full of wonder and it's waiting to be explored. Imagine a tiny grain of sand. Now imagine something 1,000,000 times smaller than that. That's the size of an atom, the basic building block of everything around us. But even within this tiny world lies a universe of its own, centered on the atom's nucleus. The nucleus is like a tiny sun at the heart of the atom. It's made up of even smaller particles called protons and neutrons, held together by a powerful force known as the strong nuclear force. Protons carry a positive electric charge while neutrons have no charge, making them electrically neutral. The number of protons in an atom's nucleus determines what element it is. For example, all carbon atoms have 6 protons while all oxygen atoms have 8. This number is called the atomic number. The total number of protons and neutrons in the nucleus is called the mass number. Surrounding the nucleus, like planets orbiting a star, are even tinier particles called electrons. Electrons have a negative electric charge and they are constantly in motion around the nucleus. While the nucleus is incredibly small, it contains almost all of the atom's mass. Nuclear reactions are processes that involve the nuclei of atoms. These reactions can release tremendous amounts of energy, far greater than any chemical reaction. Two fundamental types of nuclear reactions are fission and fusion. Imagine splitting a tiny drop of water and releasing a burst of heat and light that could power a city. That's the power of nuclear fission. In fission, a heavy nucleus like uranium is bombarded with neutrons. This causes the nucleus to split into smaller nuclei, releasing energy in the process. This process is used in nuclear power plants to generate electricity. Now imagine 2 tiny drops of water merging together, releasing even more energy than fission. That's nuclear fusion, the process that powers the sun. In fusion, 2 light nuclei like hydrogen combine to form a heavier nucleus such as helium. This reaction releases even more energy than fission. Fusion has the potential to provide us with a clean and nearly limitless source of energy. However, achieving controlled fusion here on Earth is a major scientific and engineering challenge that researchers are still working on. Section 4. Radioactivity, the dance of unstable atoms. Not all atoms are created equal. Some atoms have unstable nuclei that are prone to spontaneously decay, emitting particles and energy in the process. This phenomenon is known as radioactivity. Imagine a tiny grain of popcorn suddenly popping in your hand. That's similar to what happens during radioactive decay. The unstable nucleus releases energy and particles, transforming itself into a more stable configuration. There are 3 main types of radioactive decay: alpha, beta, and gamma decay. Alpha decay involves the emission of an alpha particle, which consists of 2 protons and 2 neutrons. Beta decay involves the emission of a beta particle, which is either an electron or a positron. Gamma decay involves the emission of gamma rays, which are high-energy photons. Radioactivity has both beneficial and harmful effects. It can be dangerous in high doses, but it also has important applications in medicine, industry, and scientific research. For example, radioactive isotopes are used in medical imaging to diagnose and treat diseases. Section 5. Nuclear physics in action, energy, medicine, and beyond. Nuclear physics is more than just a theoretical science. It has real-world applications that touch our lives every day, from generating electricity to treating diseases. One of the most well-known applications of nuclear physics is in energy production. Nuclear power plants use fission to generate electricity, providing a reliable and carbon-free source of power. While nuclear power has its challenges, it remains an important part of the global energy mix. In medicine, radioactive isotopes are used in a wide range of applications, from diagnosing and treating cancer to sterilizing medical equipment. Medical imaging techniques like PET scans rely on radioactive isotopes to provide detailed images of the inside of the body, helping doctors diagnose and monitor a wide range of conditions. But the potential of nuclear physics extends far beyond these current applications. Researchers are working on developing new nuclear technologies, such as fusion power, which could provide a clean and nearly limitless source of energy. The future of nuclear physics is bright, filled with possibilities for solving some of the world's most pressing challenges. As we continue to unlock the secrets of the atom's nucleus, we open doors to new discoveries and innovations that can shape a better future for all.